this video, we're going to talk about the basics of the blockchain as a technology. On its most basic level, the blockchain can be understood as a new kind of database, at least this was its original design. What's different about this database is that it's distributed. Digital databases have been around for a while now, but until recently they've been designed to centralize information on one computer or within one organization. The blockchain, though, uses a distributed network of computers to maintain a shared database. The blockchain is then a set of protocols and encryption methods that enable a network of computers to work together in securely recording data within a shared open database. This database consists of a series of encrypted blocks that contain the data. The blockchain is a continuously growing list of these blocks of data, which are linked and secured using cryptography. This makes it a trusted database, with this trust being maintained by open, secure computer code and encryption instead of any single institution. The database stores information in blocks that are linked together through hash values, with entries to this database being made by computers that all have a copy of the database and all must come to consensus about its state before they can update it. So these are three central concepts to understanding the system's workings: that of blocks and hashing, mining and proof of work, and distributed consensus. We'll go over each of these separately. In terms of its structure, a blockchain may be considered as a series of blocks of data that are securely chained together. New blocks are formed as participants create new data or wish to update existing data. These blocks are encrypted and given a hash value that represents a unique identifier of the data within that block. This hashing works by a standard algorithm being run over the block's data to compress it into a code, which is called the hash, which is unique to that document. No matter how large the file or what information is contained, it is compressed into a 64-character secure hash. This hash value can be recalculated from the underlying file, confirming that the original contents have not changed, but the reverse is not possible. Given just the hash value, you cannot recreate the block's data contained within it, which is encrypted. All blocks of data which are formed after the first block are securely chained to the previous one. This means that the hash value of the next block in the chain is dependent upon the previous one. Thus, once recorded, the data in any given block cannot be altered afterwards without the alteration of all subsequent blocks. As well as this hash pointer linking to the previous block, each block typically contains as well a timestamp so that we know what happened and when it happened. This hashing and linking of blocks makes them inherently resistant to the modification of their data, making them immutable records. You can only write data to the database, and once it's there, it's very hard to change, almost impossible. Thus, data stored on the blockchain is generally considered incorruptible. Blockchain security methods include the use of what we call public key cryptography. A public key, which is a long, random-looking string of numbers, is an address on the blockchain. Value tokens sent across the network are recorded as belonging to that address. A private key is like a password that gives its owner access to their digital assets or the means to otherwise interact with the corresponding data. A public key is associated with the private key so that anyone can make an encrypted transaction to the public key address, but that encrypted message can only be deciphered with the private key that corresponds to that public key. In such a way, effective security only requires keeping the private key private. The public key can be openly distributed without compromising security. For example, on the Bitcoin blockchain, to receive funds from another person, you use a piece of software called a wallet, which creates a public key that you give to someone else for them to send bitcoins to that address. With your corresponding private key, you can then access that address with those bitcoins on it. The blockchain is a distributed system. This means there is no centralized organization to maintain and verify the entries on the database. This database is instead maintained by a large number of computers that are incentivized to provide computing resources by earning some form of tokens in exchange. But these computer nodes in the network themselves cannot be trusted individually. Thus, it is required that the system provide a mechanism for creating consensus between scattered or distributed parties that do not need to trust each other, but just need to trust the mechanism by which their consensus has been arrived at. Any computer that is connected to the blockchain network and using a client can perform the task of validating and relaying transactions. Each of these so-called miner computers gets a copy of the blockchain, which gets downloaded automatically upon joining the network. When new entries into the database are made, these changes are automatically broadcast across the network. Mining nodes validate transactions, add them to the block they're building, and then broadcast the state of the complete block to other nodes on the network. In order to randomize the processing of blocks across the nodes, and to avoid certain service abuses, blockchains use various timestamping schemas, such as proof of work. Proof of work describes a system that requires a certain amount of resources or effort to complete an activity. Typically, this resource is computing time. As in the case of the Bitcoin blockchain, this is realized on some form of challenge, such that no one actor on the network is able to solve this challenge consistently more than everyone else on the network. Miners compete to add the next block in the chain by racing to solve a very difficult cryptographic puzzle. The first to solve the puzzle wins the lottery. As a reward for his or her efforts, the miner receives a small amount of newly minted bitcoins and a small transaction fee. A consensus algorithm, like Bitcoin's proof of work, functions to ensure that the next block in the blockchain is the one and only version of the truth, and it keeps powerful adversaries from derailing the system. Blockchains are trying to create a secure, trusted, shared database, and they do this through encryption and hashing, proof of work, and network consensus. The hashing and linking of blocks makes it difficult to go back and change a previous block once it's entered, but this alone would not be suffice to ensure that the data is truly tamper-proof. So then the proof of work system intentionally makes it computationally more difficult to alter the database, thus making it extremely difficult to alter all the blocks. On top of this, it places a distributed consensus mechanism, so that even if someone did manage to do this, their record would not match that of others, and thus would not be accepted as a valid record. So to successfully tamper with a blockchain, you would need to alter all the blocks on the chain, redo the proof of work for each block, and take control of more than 50% of the peer-to-peer network. Only then would your altered block become accepted by everyone else. On a blockchain of almost any size, this would be almost impossible to do. Indeed, the Bitcoin blockchain is very good proof of this, given that it now secures hundreds of billions of dollars using this method, without the network having yet been compromised. At the end of the day, what this technology enables is a database that is secure with automatic trust that is enabled by open source code and encryption. The data is tamper-proof. Once information is put into the database, it cannot be altered afterwards. It is a shared database, as many people across the network have a copy which is continuously being updated so that all have a single source of truth. Likewise, it is transparent, meaning that everyone can see all of the transactions and alterations made to the database if needed. Data quality and the resilience of the network is maintained by massive database replication across many different nodes on the network. No centralized official copy exists, and no user is trusted more than any other. Having started out life as simply a mechanism to enable Bitcoin, it has become increasingly recognized that this system is secure enough to work as a ledger for the recording and exchange of any value, what we now call a distributed ledger. But over the past years, blockchain has been evolving fast, from the original Bitcoin protocol to the second generation Ethereum platform, to today, to where we're in the process of building the third generation of blockchains. In this evolution, we can see how the technology is evolving from its original form as essentially just a database to becoming a fully fledged, globally distributed cloud computer. In this video, we're going to trace the past, present, and future of blockchain technology. The first blockchain was conceptualized in 2008 by an anonymous person or group known as Satoshi Nakamoto. The concept and technicalities are described in an accessible white paper termed Bitcoin, a peer-to-peer electronic cash system. These ideas were then first implemented in 2009 as a core component supporting Bitcoin, where it served as the public ledger for all transactions. The invention of the blockchain for Bitcoin made it the first digital currency to solve the double spending problem without the need of a trusted authority or central server. It was only later that we came to really separate the concept of the blockchain from that of its specific implementation as a currency in Bitcoin. We came to see that the underlying technology had a more general application beyond digital currencies in its capacity to function as a distributed ledger, tracking and recording the exchange of any forms of value. The Bitcoin design has been the inspiration for other applications and has played an important role as a relatively large-scale proof of concept. Within just a few years, the second generation of blockchains emerged, designed as a network on which developers could build applications, essentially the beginning of its evolution into a distributed virtual computer. This was made technically possible by the development of the Ethereum platform. Ethereum is an open-source, public, blockchain-based, distributed computer platform featuring smart contract functionality. It provided a decentralized, Turing-complete virtual machine, which can execute computer programs using a global network of nodes. Ethereum was initially described in a white paper by Vitalik Buterin in late 2013 with the goal of building distributed applications. The system went live almost 2 years later and has been very successful, attracting a large and dedicated community of developers, supporters, and enterprises. The important contribution of Ethereum as the second generation of blockchains is that it worked to extend the capacity of the technology from primarily being a database supporting Bitcoin to becoming more of a general platform for running decentralized applications and smart contracts, both of which we'll discuss in coming videos. As of 2018, Ethereum is the largest and most popular platform for building distributed applications on. Many different types of applications have been built on it, from social networks to identity systems, to prediction markets, and many types of financial applications. Ethereum has been a major step forward, and with its advent, it has become ever more apparent where we're heading with the technology, which is the development of a global distributed computer, a massive globally distributed cloud computing platform on which we can run any application at the scale and speed of today's major websites, with the assurance that it has the security, resilience, and trustworthiness of today's blockchains. However, the existing solutions that we have are like extremely inefficient computers. The existing blockchain infrastructure is like a really bad computer that is not able to do much except proof of concepts. Getting to the next level remains still a huge challenge that involves some original and difficult computer science, game theory, and mathematical challenges. Scalability remains at the heart of the current stage in the journey that we're on, and this is what the third generation of blockchain technologies are trying to solve. The mining required to support the Bitcoin network currently consumes more energy than many small nations, being equal to that of Denmark and costing over $1.5 billion a year in electricity. A lot of this is being fueled by cheap but dirty coal energy in China, where almost 60% of the mining is currently being done. This high energy consumption is simply not scalable to mass adoption. Ethereum and Bitcoin use a combination of technical tricks and incentives to ensure that they accurately record who owns what without a centralized authority. The problem is, it's difficult to preserve this balance whilst also growing the number of users. Currently, blockchain requires global consensus on the order and outcome of all transfers. In Ethereum, all smart contracts are stored publicly on every node of the blockchain, which has its trade-offs. The downside is that performance issues arise in that every node is calculating all the smart contracts in real time, which results in low speeds. This is clearly a cumbersome task, especially since the total number of transactions is increasing approximately every 10 to 12 seconds with each new block added. The volume of transactions is likewise an existing constraint. With cryptocurrency, speed is measured by TPS, transaction per second. The Bitcoin network theoretical maximum capacity is up to 7 transactions per second, while the Ethereum blockchain, as of 2018, can handle about 15 transactions per second. By comparison, a credit card network is capable of handling more than 20,000 transactions per second. Equally, Facebook may have about 900,000 users on the site in any given minute, meaning that it's handling about 170,000 requests per second. Another issue is that of cost. The fact that it costs some small amount to run the network, so as to pay the miners for maintaining the ledger. What we have is okay for a limited number of large transactions, such as sending money, but making a small transaction, like purchasing a coffee, could not be done by most blockchains. They simply can't, in their existing form, deal with a very large amount of microtransactions, such as would be required to enable high-volume machine-to-machine exchanges. It would prove too expensive to operate these kind of economies that involve many small exchanges. But this is exactly what many people will want to use the blockchain for in the future. In response to these constraints, a third generation of blockchain networks are currently under development. Many different organizations are currently working on building this next generation blockchain infrastructure. Such projects include Definity, Neo, EOS, IOTA, and Ethereum itself. They're each using different approaches to try and overcome existing constraints. Going into the details of how these different networks work is a bit advanced for this course, so we'll just give a brief overview to 2 of them. The Lightning Network is one such project that seeks to extend the capacities of existing blockchains. The main idea is that small and non-significant transactions do not have to be stored on the main blockchain. This is called an off-chain approach, because small transactions happen off of the main blockchain. It works by creating small communities wherein transactions can take place without each of those transactions being registered on the main blockchain. A payment channel is opened between a group of people with the funds being frozen on the main blockchain. Those members can then transact between each other using their private key to validate the transactions. This is a bit like having a tab or an IOU with the shop, where you just mark down what you've exchanged so that you don't have to update the main record in the bank each time you make a purchase. The record stays local between the members involved, before at some time settling the finances and updating the main bank record. This only requires 2 transactions on the main blockchain, one to open the transaction channel and one to close it. All other transactions happen just within the network, without it being registered on the main blockchain. This both reduces the workload on the main blockchain and makes it possible to run many very small transactions within the sub-network. As of the start of 2018, there is a proof of concept running live on the Bitcoin testnet, but the system will not be fully operational until later in the year, as is the case with most of these projects. IOTA is another example. Whereas existing blockchains are sequential chains where blocks are added in a regular, linear, chronological order, the data structure of the IOTA system is able to achieve high transactional throughput by having parallel operations. The data structure is more like a network rather than a linear chain, wherein processing and validation can take place alongside each other. The other big difference is that there are no specialized miners in this network. Every node that uses the network functions as a miner. In the IOTA network, every node making a transaction also actively participates in forming the consensus. That is to say, everyone does the mining. This means that there is no centralization of mining within the network, which is what creates bottlenecks and demands lots of energy. Likewise, with this network, there are no transaction fees for validation, and with IOTA, because it is more user-generated, the more people that use the network, the faster it becomes, which is the opposite of existing systems, and obviously makes it very scalable. There are lots of other possible approaches to overcoming existing constraints, but suffice to say, the blockchain should be understood as an emerging technology, whose existing implementation is like a large-scale proof of concept running on a very inefficient system, but through lots of experimentation and iteration will hopefully in the coming years evolve into this global distributed computer. As Melanie Swan writes in her book, first there was the mainframe PC, personal computer paradigms, and then the internet revolutionized everything. Mobile and social networking were the most recent paradigm. The current emerging paradigm for this decade could be the connected world of computing relying on blockchain cryptography. To understand this better, in the next section, we're going to talk about the blockchain in the context of the broader technological changes that are currently underway as we build the next generation of the internet, what we call the decentralized web or Web 3.0. How we understand the blockchain and where we are with it today is extremely transitory. In this respect, what we're talking about in this course when we talk about the blockchain is really this emerging IT infrastructure of a distributed global cloud computer. The next generation of blockchains will take us a step further on that journey. What we call the blockchain today is really just a very limited and often very inefficient version of this. We still have many very difficult problems to solve before we'll get there. Possibly that end state will look something like the blockchain of today, but possibly it will look